So this video is going to cover the end of Chapter 7. Chapter 7 was talking about first order circuits, but I was a little surprised that Section 7.7 is optional. According to your textbook, it has a little mark on it as an optional section. But it's a very important section. It's talking about integrators and differentiators, and these are circuits that have very many practical uses, and you should actually just recognize these circuits when you see them. And then we'll talk a little bit about Section 7.8 and 7.9, which is doing applications, and that includes the Multisim examples. Multisim is a nice tool. You gain a lot by using Multisim. So I'll do it even for when they weren't doing it. So here's the first circuit. This circuit is actually a differentiator, but I'm going to show you why it is beyond what the textbook is telling you. So, but first let's just analyze the circuit the way the textbook has it set up. So they have a capacitor in the input, not in the feedback. Whoops, let me go find my pen. My pen isn't here. Hang on. Oh, so it looks like in this computer, I'm on a different computer so that I can do Multisim. Looks like I have to be in presentation mode to use my pen. Minor inconvenience here. But anyhow, moving on. Let me get my pen. So I like that. And I don't want it to be in red, so let me switch. Annoying that I have to do it right from the start. Okay, so yes, okay, good. So we're on this circuit right now. So we are going to apply KCL to the circuit and analyze it. I'll go ahead and analyze it fully because it's nice to see more examples here. Your book doesn't tell you that this is a differentiator circuit, and it also doesn't tell you much about how it behaves. It just chunks through the math and says, okay, here's the final equation. But I'm going to go ahead and show you a little bit more beyond that. And also, this is not particularly a useful circuit right now because we're only looking at its natural response, so that you see there's no source in here. And so this circuit would only be useful for a very short period of time, for the time where it has some transient behavior. So, but anyway, the problem is to look at the transient behavior, so I'll go ahead and look at the transient behavior, and they don't really show you why it's a differentiating circuit. But anyway, let's start with what they said. So we're going to do KCL to analyze the circuit, and we're going to do the full first order differential equation glory here. So I have a node here I can analyze at, and I have a node right here I can analyze at. Let's analyze KCL at node 1. So we are going to say current out of the node equals current into the node, and when we've established our current flow directions, we have to be, this would be voltage at 1. We have to be consistent in our arrows here. So current out of the node would be V1 over R1, and it has to equal current into the node, but being consistent with our arrow directions, that's actually this voltage has to do with this voltage minus this voltage, right? And then the current there. But we also know that I in a capacitor is C dV dt, but it's actually in this case 0. The voltage here is 0 minus this voltage, which is going to make this a negative sign here. So it is actually minus C dV dt. So it's actually 0 minus C dV dt to get the current, because it's going into the node, so that would have a negative sign associated with it. So we go ahead and rearrange our terms. V1 over R1 C dV dt. And the V I'm talking about throughout here is V1 at this node. V1 of t is right here at this node. So here's our, and that equals 0. So there's our first order differential equation. We know that a differential equation of this form will have a solution V of t that will have a form like this, a e to the st, where we don't know s and t right now, so we substitute our assumed solution back into this differential equation, and we'll get c a s e to the dv, e dv dt, e boy, I'm just not. It's e to the st right here, correct? Yes. And plus a e to the st, and that's over r1 equals 0. And so the a's cancel out, the e to the st's cancel out, and we can divide both sides by c, and we're left with s plus 1 over r1c equals 0. So we know s equals minus 1 over r1c. So we still have to find out this unknown a so that we can get the full solution to that differential equation right there. And so we are given that our initial conditions there are 3 volts. So V at time 0 equals 3 volts, which equals A e to the minus t over r1c. So we find out, e to the 0 is 1, so we find out a is equal to 3. So we find out that v1 of t equals 3 e to the minus t over r1c. And when I calculate r1c, r1 right here is 20 k ohms, and c is 5 microfarads. And so it will turn out that r1 times c, which is a time constant tau, will equal 0.1 second. So now we have what that voltage is right there, but we still need to find out what's happening here. So we're going to go do KCL now at node 2. This was KCL at node 1. So now we're going to do it at node 2. So here it's going to be, I don't know, I'm gonna make my directions be the same. I guess I'll make it be the same. Current in, current out of the node. So that's V out minus, and remember there's 0 volts right here by our rules of op-amp behavior for an ideal op-amp anyway. So I'll have V out minus 0 over the feedback resistor right there will equal 0 minus, and again we will have C dV dt. So V out over our feedback, let's do the algebra, minus C dV dt. But guess what? We have what V of t is right down here, so we can substitute that in up here. And so we have V out over the feedback resistor equals minus the capacitor value, still same, and then dV dt here. So we have to do that derivative. So this is 0.1, so it's e to the minus 10t right here. And so dV dt will equal minus 30 e to the minus 10t. So that will now be minus 30 e to the minus 10t. And we have that value right there. So finally we get V out equals, and you multiply everything together that we need to multiply, and you'll get the answer of 12 e to the minus 10t. And so that's what V out is, and it just looks like a decaying signal. So I went ahead and simulated that because there's more to this problem that's useful. So let me, how do I get out of the power? I want to get out of the PowerPoint mode. Actually, I'd like to pause, and I don't even see my controls anywhere. Oh, so annoying. Okay, I'm still recording. I'm okay. All right. Sorry. It's a different computer. It's not quite as friendly. So anyway, I put this circuit in Multisim so that you can see it. There's a few things that you have to do to run this simulation. So this is going to be a transient analysis that we're doing because we have no sources in the filter. So one thing is when I put the capacitor in there, I made sure I picked one that had a polarity on it, because it mattered which way we put the 3 volts. The next thing is when I change the values of the capacitor. Ooh, so let me use my pen here. Nah, doesn't work. Sorry. Okay, so when I change the value of the capacitor, I am also allowed down here to put initial conditions. So I put the initial conditions as being at 3 volts. So that's good. And I think I can zoom in here. Maybe. Nope, I can't. Okay, so that's good. Now the next thing we want to do is we're going to do a transient analysis. So I'm going to go over here to the analyses, and there's an option here for transient analyses. Boy, I hope you can see, guys can see this. So the transient analysis will allow us to pick our start time, which I said 0, and this time my end time I made it 0.1 second. Now I knew that the time constant is 0.1 second. Maybe I want to make it 0.5 seconds, so I have 5 time constants. The other thing that you have to check for is these initial conditions. The default value will be to automatically determine, but I found out that that didn't work, so you want to make sure you select the user-defined initial conditions. So now you have to say what you want to look at for an output. I want to look at voltage at node 6 as my output, so I moved it over here. I do have my nodes displaying on my circuit, so this is node 6 is where the output voltage is. And I used a 741 op amp, which is the same one as you're doing in lab. Okay, so that's all it takes to do a setup for transient analysis. So when I simulate, there's the answer. It's a decaying exponential, just like the math told us it was. So, gee, why do we have it as an op amp? Because, you know, I could have had a decaying exponential with just an RC circuit. So in a way, this wasn't a very informative problem. So let me show you a few other things that I think are interesting to do with this problem. So one thing is seeing how it behaves. I said it was a differentiating circuit, so let's make it be a differentiating circuit and change the input. So the first thing I'm going to do is I'm going to get rid of this, the fact that I've grounded out the input here, because this would normally be the input. So I'm going to get rid of that. And one of the things I'm going to do now is I'm going to, in my simulation, there are instruments. So there are some instrumentation, here I made it a little bigger, some instrumentation choices that you can have. So under Simulate, Instruments, there is a function generator that I can pick. So I'm going to put a function generator in, and then look at what my function generator choices are. So I can change from sine, triangle to a square wave. So it's a differentiator. I'm going to try triangle first. I'm going to set the frequency to be 500 hertz. So I set 500 hertz because I know right now that my time constant is 1 millisecond. 1 millisecond corresponds to, if you invert that period, that would correspond to a 1 kHz signal. But I want to see at least 5 time constants go by, so I'm going to slow the frequency down to, actually, instead of being 500 hertz, I think it might be nice to see it at 200 hertz. So let's do that. 50% duty cycle. I don't need a very big signal because in the absence of a it probably has plenty of gain in this circuit with that 80K feedback resistor. So I'm going to make it 1 volt peak, and I'm going to give it an offset of a half a volt so that it goes 0 to 1 volt all the time. Okay, so that was my settings. Now you want to ground the middle terminal here, just like you would set it up in lab. There it is. And this is my input signal. I'm going to wrap it around and apply it to the capacitor. Now how we want to look at the output, back in my instruments, I'm going to place an oscilloscope here in the output. There's my output. I needed a ground, just like you do in the lab. You need a ground. And here's another ground. I'm going to look at two channels because I'm going to look at both the input and the output. So let me run this A to the input over here. Oops, try again. I'm going to run A to the input. So now I'm connected to the input, and B, I want to look at the output. In order, also a just a little helpful tidbit here. If you want to see your oscilloscope display in different colors, you can change this color. Just double click on that wire and change the color, and it will also change the color on your oscilloscope display. Okay, so I'm not going to do a transient analysis this time. I'm actually just going to run, no particular kind of analysis, because my oscilloscope's going to look at everything. And so sorry I paused it for a moment because I didn't like the results that I was getting in the simulation, because I wanted you to see that this was actually behaving as a differentiator. So what I did do is I changed a couple of the values here because I wanted to slow this circuit down a little bit so that you could see its function on the oscilloscope. So by slowing it down, I made the time constant be smaller, right? Or actually the time constant is a bigger number. So this, instead of being 80 k ohms, is only 220 now, and I made a bigger capacitor here. And the other thing I did was I changed my frequency to go slower because I want you to see that this behaves as a differentiator. So then I changed this output line to be yellow because it shows up better on my oscilloscope display. So when I run this circuit, this is what I get on the simulation now. The yellow is the output and the red was my ramp input. So if you look at, consider this, right? You have, what's the derivative of a ramp? The derivative of a ramp would just be a constant number. So, and there's a gain factor in here that has to do with the R and the C. I'll analyze this here for you in a moment, the exact circuit. So this is going to have an inverting kind of a configuration, but derivative of a ramp will be a number, and the derivative of the negative ramp will be a number. And I have a little oscillations going on in here, which just has to do with the stability of this circuit. It's not really the best circuit as drawn. There is a better way to draw that. It would usually have an input resistance and another resistor in parallel with the that would be the integrator. So there would usually be an input resistor to help with some of these stability issues. But truly, the derivative of a ramp should be a step, and that's what we're seeing right here. So I'll go ahead and analyze this so that you can see what it's doing. So back to my PowerPoint here. The circuit's a little bit different. So here's the new circuit that we'll be looking at, because I want you to see it behaving as truly as a differentiator. So let me put the circuit on here for the sake of us analyzing it. So here it is with its values. We're going to go ahead and analyze it. So for me to do that, I got to go back in presentation mode. Okay, so let's go ahead and analyze it. Okay, so for this circuit, we have a V here, and we can have a C dV dt, and then it would be equal to, current in equals current out. So if I do that for this circuit, it's C dV dt equals, watching my signs now, I'm going this way, so it's minus V out over the feedback resistor. Okay, so then but we have V of t right here. So my V of t, rather than it being a differential equation that we have to solve for, is this ramp function that I had. So my ramp function was running at I forgot my frequency now. Now I have to go back and look. So my ramp function was running at 100 hertz and 1 volt peak with a little offset in there. I should have run that as a without the offset. Same solution in the end. So 100 hertz and 1 volt peak, or 2 volts peak to peak. So we'll look at that here. Back to our problem that we're doing right here. So it was a ramp, so the ramp looked like oh crap. My ramp looked like this. Doesn't matter, we'll probably get the same solution if we take the DC offset off, because the capacitor blocks the DC. So it's 1 volt, 1 volt, and since I was running at 100 hertz, 100 hertz means that the period of this waveform is 1 over 100 seconds, which is 0.01 seconds. So that means for 1/2 of the period, the slope is from here to here. I'm going to go from the change in the y direction, which is going to be 2 over the time that it takes, 0.01, so that would be 200. And then the other half of the period, when I'm in the negative side, then my slope would be minus 200. So I could say it's a 200 ramp of t, for example, in our notation. So so my C was 50 microfarads. B out equals minus R feedback C dV dt. So minus R feedback is 220 ohms, and then my C was 50 microfarads, and then dV dt, which is a derivative of a ramp function, and a derivative of a ramp function is going to be a step function. So 220. I'm doing calculating that number right now. So that will equal 0.011 dV dt. And dV dt is the derivative of the ramp function. So it's going to, if we just look at one period right now, 0.11 times 200 u of t, that's 1/2 of the cycle. The other half of the cycle with a time shift, minus 0.011 times, the slope is minus 200, and it would be u at t minus 0.01. Whoops, yeah, 0.01. So that's what V out should be. And if we go back and we look at what we got, this should be 2.2 volts. This right here is 2.2 volts. So if we go back and look at what we got, boy, that's a little bit annoying. So we go back and look at what we got right here, and we look at the waveform that was produced when we ran the simulation. Here it is. Channel 1 is in 1 volt per division, so that's up 2 volts. channel B is in 5 volts per division. So, ooh, I'm off by a factor of 2. So I'm going up 4 and down 4. Ooh, I could find that somewhere. But the point really is that the ramp function, the derivative of a ramp, is a step function, and we indeed see that in the circuit. So I actually do see where that mistake is. Mistake is right here, that you probably caught it. The ramp is going up, the ramp is going down. The complete period is 0.01 seconds, but half a period right here is not 0.01 but 0.005 seconds. So that would make this be 400 and not 200, and then I indeed get my amplitude as being 4.4 volts, which, yay, matches what I'm seeing on the oscilloscope, and my differentiator is behaving as a differentiator. This was the next example problem in your textbook. I think they intended this to be an integrator, but they do not have it with any source in there, so it's not very illustrative as an integrator. So let's go ahead. There was no solution for this problem in your textbook, so I thought I would go ahead and work this problem. So I have this resistor value and this capacitor value. This was an odd problem, and they give you an initial voltage of I saw it there, 4 volts across this capacitor, which is it's a little bit of an odd problem because you see this is at 0 volts, and this means that's at 0 volts. So that would actually make this be a negative down here. And that if this is at 0 volts and this side is at 0 volts, then this resistor absolutely has nothing to do with the circuit. So all we're really looking at is this part right here, which is, and we have essentially a ground right there in the circuit and an initial charge on this capacitor, and we know how to analyze that type circuit already. We already know that the V right here, which would be V out, same as V out, the V out is going to have some kind of A e to the st form, and we have an R and a C together, and we can actually write that down. It's a discharging capacitor circuit, and we could actually write that down by inspection, knowing that this is 4 volts. Well, this point is 4 volts higher than this point, so there, and this is at 0, so therefore that's at -4. That's its additional voltage, and we know that it's an e to the minus t over RC solution. R times C in this case is just 50 k ohms, and C was 10 microfarads, and that would end up equaling 0.5 seconds. So V out as a function of time equals -4. That was the only really trick to this problem, but otherwise it was a problem by inspection, e to the minus 2t. So it didn't really have anything to do whatsoever with the op amp, so instead I will show you what an integrating circuit does. So to demonstrate the integrator to you, I actually swapped the positions of the capacitor and the resistor here. So the capacitor is in the feedback right now, and the resistor is on the input. The other thing I did was I changed this capacitor value here. Now this configuration of an integrator is kind of an unstable circuit, and usually we have another resistor in parallel with this capacitor here, like the example I just did before. So now I'm driving this circuit with a step function, because if you integrate a step function you should get a ramp function, correct? So that's what I'm driving it with. So my input right here is this step function that's going back and forth between 1 volt and minus 1 volt. But truly, when I see a plus 1 volt input, I have, because this is an inverting configuration, I have a negative ramp. And vice versa, when the negative input is in here, I have a positive ramp. So that's an integrator circuit behaving as an integrator. There I'm running it. You can see, oops, I'm on single sweep. So there I'm running it, and I can expand it or whatever have you. So this is an integrator circuit, and indeed it's converting the step function into a ramp function with a negative sign because this is an inverting configuration. So